Good evening, everyone. A very warm welcome on behalf of ISRO Speech Studio KIYE. I'm Shivani, an active student coordinator from Kalam's Institute of Youth Excellence. I'm delighted to be a host for third lecture of S Talks, Science and Technology Talks. In our previous lecture, we had the honor of initiating the lecture series with Dr. B. Chiranjeevi Fanindra sir, founder and CEO of Cosmos Space, who delivered an engaging and insightful session. He shared valuable knowledge that captivated the audience and received a remarkably positive response. His expertise, combined with an interactive and dynamic presentation style, made the session highly informative and inspiring. Absolutely incredible, right? And even students, educators, and institutions from all over the country united with us in learning and exploration. And it became clear that curiosity for space and technology has no boundaries. We meet every Saturday. Yes, you heard it right. Every single Saturday, we come together to learn, explore, and grow. More connection, more consistency, more impact. KYE provides S Talks that is not just a lecture series, it's a platform, a community, and most importantly, a mission to ignite curiosity, to inspire innovation, and to shape the future of young minds. Our theme is Space is the next destination. Let's explore it together. STOCKS S means science and technology. It is an initiative dedicated to inspiring young minds towards space, aerospace, and futuristic technologies. Imagine learning from some of the brightest scientific minds every week. Think of being part of a moment that builds the next generation of scientists and innovators. A year long online lecture series every Saturday, 6 p.m. to 7 p.m. 52 lecturers, 52 speakers, 52 topics, 52 hours of knowledge and inspiration. This is not just a lecture series, it's a mission to ignite curiosity and to shape the future. Here's what you gain from S Talks. Learn directly from top scientists and industry leaders. Explore careers in space, aerospace, and emerging technologies. Build communication and critical thinking skills. And earn certification after completing all sessions. Let's now take a quick look at a short audio-visual presentation that showcases the vision, achievements, and impact of KIYE. Now the video starts. Next, I would like to invite our passionate student coordinator, Miss Mayuri, to share her experience in KIYE. Mayuri, please go ahead.
Thank you, Shivani. Good evening, everyone. I am Mayuri, and I'm glad to share my journey as a student coordinator at Kalam's Institute of Youth Excellence, an organization inspiring youth since 2013. Being part of KIYE has been a wonderful learning experience. It helped me improve my leadership, teamwork, communication, and coordination skills. One of my first experiences was volunteering at Inspire Hyderabad 2K24 at Gachibowli Indoor Stadium. During this event, I had the opportunity to listen to Dr. Somnath sir. Later, I participated in Vigyan Vaibhav 2K25 organized on National Science Day at Gachibowli Stadium, where thousands of students attended. We also had the opportunity to witness the presence of Honorable Chief Minister Sir Revant Reddy Sir and Raksha Mantri of India, Honorable Rajnath Singh Sir. During the event, I took responsibility for maintaining the crowd and also experienced live science models and an impressive drone show. Another memorable event was the Kalam Space Convention 2K25 at GMR Arena, Shamshabad, conducted on the eve of APJ Abdul Kalam's birthday. The first time we got the opportunity to see astronaut Subhanshu Shukla sir in person. Recently, during Vigyan Vaibhav 2K26 on 28th February, I coordinated students from Railway School and managed around 300 students. It was a wonderful experience seeing their excitement while learning about space science and observing innovative scientific models. The event was honored by the presence of Subhanshu Shukla sir, G. Satish Reddy sir, and several scientists. Through these experiences, KIYE has given me great opportunities to learn, volunteer, and even grow. I truly encourage every student to join KIYE and explore their potential. Finally, I would like to express my sincere gratitude to our chief mentor, G. Satish Reddy sir, Naresh Indian sir, and all the ISRO space tutors for their constant guidance and support. Thank you. Jai Hind.
Thank you, Mayuri, for your dedication towards KIYE and sharing your experience with us. Let's make this session interactive. Dr. Vasudevan Gnana Gandhi sir will soon address your questions and doubts related to space and aerospace. As it is the incredible lecture of S-Talk series, you will be meeting and sharing your questions with him soon. Now comes the highlight of today's event, the moment we have all been eagerly waiting for. Today, I am truly honored to introduce an eminent personality in the field of cryogenic rocketry, Dr. V. Gnana Gandhi sir, whose remarkable contributions have played a vital role in shaping India's space program. With a career spanning over 5 decades at the prestigious Indian Space Research Organization, Dr. Vasudevan Gnana Gandhi sir has made outstanding contributions in the field of rocket propulsion, working extensively across solid, liquid, and cryogenic rocket systems. His journey reflects exceptional dedication, technical brilliance, and unwavering commitment to advancing technology. He completed his graduation in mechanical from Tagraj College of Engineering and joined in ISRO in 1968. Over the years, he has served in several key leadership roles, including Project Director for Cryogenic Systems, Cryogenic Projects, and Associate Director at Liquid Propulsion Systems Center. Dr. Vasudevan Gnana Gandhi sir was instrumental in major international collaborations, including the cooperation of Vikas engine technology from France between 1976 and 1979, and cryogenic technology from Russia in 1993. His pioneering efforts laid the foundation for India's cryogenic rocket technology, and under his leadership, the cryogenic upper stage engine was successfully developed and tested, marking a significant milestone in India's space journey. In recognition of his exceptional contributions, he was honored with the ASI Award in 2002 and was conferred the prestigious Padma Shri by the Government of India. Beyond ISRO, he continues to contribute to innovation and technology. He is actively involved in the development of hydrogen powered buses in collaboration with Tata Motors and currently serves as the Senior Vice President at Skyroot Aerospace, where he is contributing to the development of launch vehicles for small satellites. Apart from his technical achievements, he is deeply passionate about inspiring young minds and frequently engages with students as an aspiring scientist mentor. His journey is a true testament to show how vision, perseverance, and innovation can transform nations' capabilities in space technology. We are deeply privileged to have you with us today, sir. Sir, the virtual stage is all yours.
Good evening to all. It's very nice to meet the young mind, those who are interested on science, specifically space. I am very happy to meet all of you. Well, I can share some of my experience. As he told, 1968, I joined in ISRO, and maybe those days, and Sarabhai was there. So I started my career under him, and it was very interesting. So from nothing, there was nothing, no technology, nothing. So from scratch, we started working on rocket. Maybe you will see some of my thing. I will share my small presentation, and of course, to the end, you can take a lot of time to have a interaction session, so we can have a section for that. Okay. Are you seeing my screen?
Yes, sir, we can see.
Okay, thank you. So, as I said, I started joining in ISRO. At that time, it is called the Space Science and Technology Center. It is not VSSC, SSTC. Very nice, a small town, Trivandrum, and near the seashore. So we launch small rockets. At that time, it's called Rohini series. We call it Rohini 75, 100, 125, 200, 560. You may be asking why this number 75, 100, 120. This is the diameter of the rocket. And mostly the nearest industrial town is Ernakulam. There was a aluminium factory. There, the extrusion pipe, the aluminium pipe available sizes are 75, 100, 125. So we purchase, we load the propellant. I was handling little dangerous mixing of the propellant and loading it inside the rocket and testing. So many times ended with a lot of explosions and burnings and all those things. Well, initially the solid motor time, I learned a lot. All of you know that anything to burn, we require a fuel and a oxidizer. If a fuel and oxidizer both are in the solid form, we call it solid rocket. If both are in the liquid form, we call it liquid rocket. We are all air breathing engines, including human beings and trees or plants and everything. We breathe air. Of course, we take, some of you may be taking solid food like idli or dosa at the morning. Some people may take some juice. So we breathe, oxygen is going, and we burn in the cells and other things. Rocket also similar, right? Then you may even automobiles and aircrafts also air breathing engines, but they carry only the fuel because they are all operating in the atmosphere region, so they can take the oxygen from the air. But rocket has to go above 50 kilometers. There is no air, so we have to carry both. So as I said, if it is solid propellant, it is both are in the same form. So you could see initially in ISRO, as I said, 200, RH300 and RH560. And we tried to launch from Trivandrum up to 200 dia. Then later, due to safety reasons, we selected a good spaceport near Chennai, that is Sririkota, and it was an island. So we shifted all our launching site to that site. But the government is very clean in the sense there is no point in developing like Americans and Russians because they are in the space race. So many rockets and many engines. But the demand, the requirement, what is that? Is very clean or very clear in the sense we require a satellite around 500 to 1000 kilometer altitude, and it should have a very big electronic eye like a camera. So it should observe the land or the earth, what is moving, what is going on, and what is the erosion of the soil, or any movement in the border, or all those things. So we require a remote sensing satellite, Indian Remote Sensing Satellite, IRS. So to put that satellite, the government asked ISRO to develop a rocket. Similarly, if you put any satellite at 36,000 kilometer, the speed of the satellite at 36,000 kilometer is equivalent to surface speed of the Earth. So anything at 36,000 kilometer will move along with us. When you move, the Earth moves. The India is moving. So the satellite also always above you. That is required for our communication purpose, like a TV or a telephone or all those things. Maybe even weather also. And ERS also, we can do the weather and other things and navigation and so many things. So there are two requirements. One is a satellite to put in the low Earth orbit the satellite. Another one is the synchronous satellite. So we call it PSLV for the smaller one, and GSLV, Geosynchronous Launch Vehicle. And that time, the payload is only around 2000 kg, but the demand is more, maybe up to 4000 or 5000 kg it has to carry. So we have augmented the GSLV into GSLV Mark II, Mark III, like that. So now currently the rightmost one, what you are seeing, Mark III, is the biggest one. In the same one only we are planning to send the astronaut also future in maybe another 1 or 2 years time. And well, I am a propulsion engineer, as she was introducing me. And when I joined, as I said, the solid motor. And what is propulsion? So I am showing a small squid or a small fish, which takes the water and expel from the back for its movement. So that is the principle in rocket. When you expel the hot gas, you get the forward movement. So like that it starts. So maybe rocket propulsion, if you take the first three, solid, liquid, and hybrid, we call it chemical propulsion. Then of course nuclear and solar. Maybe currently ISRO, we are working, or ISRO, or even now private companies, we are all working on solid and liquid, hybrid, little bit. Long back we started, but not much. And nuclear, of course, towards the end of my career, I presented a paper also, but maybe they are waiting for youngsters like you guys. You can come and start the work. Solar also nothing we could do much. I think these areas is still to be explored. Maybe Americans and Russians, they have done some work on nuclear propulsion and they have developed the engine also. But due to safety reasons, they are not allowed to launch. So it's are all already available. And solar, specifically for interplanetary missions and other thing, we require small thrust, but there is nothing, LNG is required. So that area also people are working. Maybe I think it is good, and youngsters like you can spend some time. So I said solid propulsion is a very simple, very simple. Is having a tube, kind of a long length cylindrical tube made out of very strong materials like 15 CV6 or maraging steel, or even now currently where I am working, we are all using carbon fibers. So with that, we will make the good cylindrical portion, and it will have a head end, and it's having a nozzle. Of course, I'll explain it later. It has a lot of good advantage and disadvantages. Advantage is it is ready even for some missiles and other things. If you want to use, it is readily available, so you can use it. Disadvantage is if any problem occurred in this one, the whole rocket we have to lose it, like cracks or fold or whatever this thing. And as I told, anything to oxidizer and fuel. So the polymeric binder and the oxidizer. In between, I have put a metallic fuel. So initially, we started with ammonium perchlorate as the oxidizer and polymeric binder, any fuel which is having a highly viscous fuel like rubber or tar or even PVC, liquid PVC can be mixed with N2O4, uh, ammonium perchlorate, we can make the rocket faster. But the temperature is not that high. So you youngsters, you might have played during Deepavali time crackers. You might have seen your hand always, wetted with aluminum powder. So the aluminum powder can burn as a fuel. So we can mix this aluminum powder also along with the solid propellant. It gives a better efficiency. So in ISRO, you can see here oxidizer, generally ammonium perchlorate. We have a biggest facility in Kerala. And metallic fuel, aluminum powder. Of course, Tamil Nadu, a lot of crackers manufacturing is near Sivagasi. They have a big aluminum powder, so we buy from them. And polymeric binder, even though I said tar and PVC, all are very old. Now, currently, what we are using is carboxy terminated polybutadiene or hydroxyl terminated polybutadiene and P-bond, all these three things mainly we are now currently using for our PSLV and GSLV program. Initially, we work little bit on defense side, in the aircraft to take off. We make small rockets, and now I said the fiber also can be used. ISRO, long back when Kalam is there, he started working with fiber reinforced composite. So the motor case, what you are seeing yellow color is composite material, which is the one now currently third stage of PSLV, which is powering. And this is the strap-on for the PSLV. You could see the cross section of the solid motor and the black line on the like a tube, and the cross section what I have shown is the propellant. So throughout the length there is a port, and left side there is an igniter. So when the igniter is initiated, it will fire, and then you will get the hot gases. You could see now the diameter of the rocket is almost like 2.65 or 2.8 meter diameter. So people can go inside and insulate, and the flame should not spoil the casing. So like that. So the rocket, what you are seeing, solid motor, the inside will be like this. Whatever you are seeing, the gray color is the propellant, and the shape is the shape. Through that, the gases burns and it comes out. And you could see the nozzle and along this one. This is the biggest 200-ton propellant it can have it. This is the one now currently GSLV Mark III, two numbers strap-on. It is using on both sides and it is powering. So this is about the solid. You could see much earlier, not nowadays we are not doing the ground test because we have already proven. So before we flight test, one or two numbers, we will do it in the ground. Like a doctor, we will check the pressure and temperature and all those things of these motor cases and how much thrust it produces. So we have a test facility at Sririkota. So we do the test also here. This is about a little bit about the, I worked initially for 8 to 9 years on solid propellant. Then I switched over to liquid. All of you know that even though Chinese or Tipu or all those people older days, they've done the rocket principle some work. But very workable one, the modern rocket is first made by the Germans during the Second World War. The rocket is called V2 rocket. They launched many and to destroy, some of the enemies and kind of thing. So Hitler was having a very big factory in a big cave. One side raw material goes, other side missiles will come out, V2 rockets. And once the war is over, and most of the engineers were taken by Americans, and some of the technicians taken by the Russians, very few people they have come to France. I am also lucky enough to work under them for 3 years in France. And we have come back and we started working engine called Vikas engine. So in liquid rocket, just now I have explained about the solid rocket, but in liquid rocket, like our fuel tank in car, there is a fuel tank. Since I said above 50 kilometers, there is no oxidation. We carry the oxidation also. Both are in the liquid. So there are two tanks. And in the bottommost, we have a engine separately, like IC engine in car. We are also having a rocket engine. You might have seen your grandmother might have used wood for cooking and later kerosene. Somebody pressurized. So anything burns under high pressure, the energy release is high. So in rocket also, we burn the propellant and both fuel and oxidizer at very high pressure. Of course, in India, we pressurize the burn at around 60 to 70 bar. In the car tire, normally it will be around 1.2 bar or 1.3 bar. So here it is 50 to 60. Of course, now current engines by Americans and Russians, it is going up to 300 bar also, or 200 to 250 bar. We have not yet reached to that level, but we have up to 60 bar or 70 bar level we have gone. So this is if you want to burn at 60 bar, if you pressurize the tank weight will be so high. So in between, we will put pumps. I have put a fuel pump and an oxidizer pump. So the pump, like in your house, you have a water pump to raise the water from ground to your upper tank. It may be a quarter horsepower or half an horsepower or 1 horsepower, or you might have seen in the field, a lot of water pumps are working. Same way, here also a centrifugal pump, but in ground we have electricity, we can use motor. But in air, so we don't, we require a prime mover. So there is we call it a turbine. So a turbine runs these two pumps. The turbine also has to be run by something, a hot gases. So we have a gas generator. The gas generator generates hot gas that runs the turbine. So all these things put together, we call it turbo pump. This turbo pump feeds the propellant to the combustion chamber. So that is what the difference between solid and liquid. So in LPSC, we made a lot of engines, very small thrusters, 1 Newton in even 11, 22, 50, all those things are used in satellite. If you want to keep the satellite in proper position, we require all the corners of the satellite at small thrusters. I said IRS, Indian remote sensing satellites, which are very low orbit, we use 1 Newton and 11 Newton thrusters. And our all INSAT satellites at 36,000 kilometers, we use 22 Newton thrusters for stabilization. And 50 Newton is for roll control and other thing. This 440 Newton, very interesting. I think you or moon mission and even putting the satellite in 36,000 kilometers, all those things. This 440 Newton is working for a long duration, maybe around 3,000 seconds. Many times it will be start and restart. And similarly, the 6.4 kilonewton is for PSLV first stage pitch and yaw control. The second one, 7.35 kilonewton, is the PSLV fourth stage. 75 kilonewton, that is a cryo engine, first one I built. Okay, later we will see that one. And the last one is a 70 ton or 73 ton Vikas engine. This is the one from France. We have come back and we did the work. And you could see the combustion chamber, as I explained, both fuel and oxidizer comes and burns. So anything to mix properly, because I said the 73 ton, nearly about 250 kg of propellant has to be burnt at 1 second. So how to mix properly? So there is a big injector, you could see here, and that injector is having more than 740 holes, and this is the combustion chamber where the hot gas. The core of the combustion chamber, the temperature will be approximately 3000 degrees Celsius. So no material could withstood. So we have to have some film cooling and the walls. In addition to that, we use super alloys. What is super alloy? The material, generally even stainless steel or any other material, if you heat, the strength will come down. But there are certain materials, even if it is high temperature, the strength will not come down. That materials are called superalloys. Here we use KC20WN or Highness 25. That is a similar one. We have already indigenized in Midani in Hyderabad itself. So they are now supplying. This is the turbo pump, what I explained. I said the centrifugal pump. One is N2O4 and another one is for UDMH. N2O4 is nitrogen tetroxide, that is a liquid oxidizer. O, it is the oxygen donor. And UDMH is unsymmetrical dimethyl hydrazine. It is a hydrazine family. Both are not, it's a good propellant because it is hypergolic. Even it touches, it will burn. But both are not environment friendly. Both are having a lot of issues to store and handling and all those things. It's very dangerous. So all other countries, they are replacing with semi-cryogenic engines and full cryogenic and other thing. We are also now currently working to replace this engine to this one. So this is a schematic of Vikas engine, and sorry. So this is the stage. So you could see the maybe engine test. Okay. So this is the stage N2O4 tank, and these tanks are all made out of aluminium. Bottom you are seeing the Vikas engine. This is for PSLV second stage as well as for Mark II also GSLV this is used, or even L40 also. So some of the tests we conduct at Mahendragiri like this. This is the PS4 engine already I explained. And we have the PS4 stage, that is the PSLV fourth stage. You could see the left hand side is the tank is made out of titanium. Titanium is having a very good strength, so it's very costly. Even one tank may cost nowadays maybe 10 crore. And two engines are attached, and it is powering the PSLV fourth stage. So this is the test long back we have conducted at this one. Then 1985, I think after the Vikas engine is very successful, I was asked to start the cryo program. Okay, Mr. Nambudri was also there, and I also started with him. So like solid motor, what we have done, we started with gaseous oxygen and gaseous hydrogen. And you could see I started with a small bench type using gaseous hydrogen and gaseous oxygen. And initially I had a lot of issues. Finally, you could see the small patch, the one. I tried to do the single element and graduated slowly using liquid oxygen and gaseous hydrogen, and later liquid oxygen and hydrogen plant I have put in Mahendragiri and fired. At that time, it was 17 elements with developing 1 ton. So 2 or 3 explosions. Finally, I understood the reasons, and finally we cleared it, all those things. Successfully, I fired a 1 ton cryo engine, and government was, our chairman was very happy, and they started giving me good project money to do 12-ton engine. By the time the Russians came, then they said, why you are struggling, we will give the technology. So I was the project lead to go to Russia to acquire the technology of cryogenic. So you may ask, if these engines are working, why do you want cryogenic, which is very, very low temperature? If you say liquid hydrogen is 22 Kelvin, you see zero, if you are going, that is minus 252 degree minus Celsius in your house fridge. Maximum it may go to minus 20 or minus 4 or minus 5. But here it has to go to minus 250 degrees Celsius. So why do you want such a thing? And if you see here, the specific impulse or the ISP, that is the one which is proportional to the temperature, but inversely proportional to the molecular weight. If you see the periodic table, hydrogen is atomic number 1. So the lowest molecular weight is hydrogen. If you use the hydrogen, you get the highest specific impulse. Or we will say normally 1 kg of propellant, if you burn, how much thrust you will get. So in solid, we may get around 280 to 90 kg. In liquid, up to 310 or 320. In cryogenic, full cryogenic, that is with liquid hydrogen and liquid oxygen, we get around 445 to 456. That's why we go for hydrogen. This is the cryo stage, and this is the first engine I built. And most of the components, the turbo pumps, are all made in MTAR or MTAR, which is in Balanagar in Hyderabad. The whole combustion chamber is made at Godrej, and these are all the elements of the injector to this is the combustion chamber, inner made out of copper. You could see the how the copper is small channels are there. Outer there will be a stainless steel, and this is braced in a furnace. And this is the turbo pump like Vikas engine. But one thing is, even though hydrogen is very good, the density is so low. So if you want to pump, you have to run a very high speed. Here in Vikas engine, it is only 10,000 RPM. But here in nearly about 45 to 46,000 RPM. So the moment you go to very high speed, lot of issues. Here the bearings has to be cooled by its own propellant, not by any grease or anything. So this is also a challenging work, and we got the technology from Russians, and we manufactured, and this is the first engine, and Anna University students, they made the 3D printing. And when I was there in Russia, maybe due to geopolitical reasons, we were not allowed to stay for more time. So we came back, and I submitted a project report. The government was happy to give 300 crore to start the cryo program. Out of that, 100 crore I spent for the test facility, and night and day we struggled. Finally, we could make. This is one of the hydrogen facility at Mahendragiri near Kanyakumari. This is from naphtha. We take the hydrogen, and with the air, liquid air, and separated, and then liquid nitrogen, it cools, and with Joule-Thomson effect, we take the hydrogen. So this is the test facility at Mahendragiri for liquid hydrogen and liquid oxygen, and these are all established in 1995, 96, or 97 time. And this is our control room, and this is the first engine. Okay, I'm sorry. And this is a cryo engine, and I fired in 2002, and it went well. So this is the way cryogenic program was successfully completed. By the time my age is also around 60, 62, so they asked me to retire. So I thought I have spent a lot of money of the common man for developing this engine. What to do? So I love hydrogen so much. So what to do with the hydrogen for common man? I thought today you are seeing in Delhi a lot of pollution problem due to automobiles and this and that. So if you use hydrogen in the automobile, and hydrogen, if it goes through the fuel cell, I think all of you might have known by this time. So there is this is a solid electrolyte, proton membrane is called Nafion, and it is a modified Teflon, and you could see here the proton only will be allowed through this one. So the electrons are stripped as a load, and outlet with H plus from the air, we pump the oxygen, it joins, and only water is the H2O is the product. So there is no pollution. So I thought, why not I will run hydrogen using and fuel cell. So ISRO, they gave me after retirement a crore, and Tata Motors, they gave 5 crore. With a 6 crore with the Tata people, I started this work in Bangalore as well as in Mahendragiri. This is a Mahendragiri one test place where we have conducted all the tests. And this is the bus I run in 2015 at Mahendragiri. With the right side, what you are seeing is Alagvelu, the chief of the Mahendragiri, and the spexman is Dr. Raja from Tata Motors, left side myself I am staying. So this is the bus, and luckily no problem. I run this bus in Mahendrari more than 4 or 5 kilometers. Afterwards, the same bus was running in Ahmedabad more than a lakh kilometer. Well, still the government has not approved hydrogen as the automobile fuel. We could not pursue further. After the retirement, I joined in Skyroot. She said I am working there, and it's a private company, and we are making. I am in charge for the liquid side for control rockets and see the test, and we conducted near medial test facility in Hyderabad. This is the one which is going to roll control for initial stage of this one. This is the stage, and fourth stage is a OIM stage. That's orbital adjustment module, and this also I am in charge for that. Now currently this also ready. You could see 3D painting. This is the actual hardware. We have conducted one test. Now the system is ready for flight. Maybe in another 1 or 2 months' time, we are planning to launch the first biggest rocket by an independent private company to launch this other than ISRO. And during this time, I take a lot of interest in 3D printing, and whatever work we have done in ISRO, the combustion chamber has that copper inside, outside is stainless steel, which is braced and all those things, very complicated. Now technology has improved with the channels and other thing. A single piece can be printed. So I was fascinated and I started the work in this new company. So you could see I started a cryogenic engine also here using liquid oxygen and LNG, not LH2. LH2, even though I like hydrogen, as I said, but hydrogen is not available in the air or not plenty. Either you have to split water or hydrocarbons. And when you make it to liquid hydrogen, the cost will go to per kilo 6,000, 7,000 rupees. So for a company like a private, it is not good. So I thought, why not we'll use LNG as the it's a fuel. So I did the first test also. And you could see the we call it Dawari 2. And now Dawari 2 also I have completed. And this test was conducted on Rocket 2 and more than 200
Three, two, one.
So it's a big problem with liquid oxygen and LNG. So that work also I have almost completed. Well, now youngsters, because you are all here, we are polluting the space also with a lot of satellites and debris and all those things. And more than 1 lakh pieces are going around and other thing. Somebody has to sweep, somebody has to remove. So people are working started, and I hope youngsters you also take some interest how to clean this debris in space. There are some techniques, maybe you can think about it. For youngsters like you, I thought, and you have to work hard. Don't work for the hard boss. Boss is coming, you do something. No, you do for your no interest. I always believe in teamwork. Sometimes if you work, you are the only person working. Many people may be watching. Don't worry about it. That is, you have to do the work. Maybe the goal to achieve the diamond is very close. There's below if you see, but he is so tired and he is returning. Don't do that. You have to persistently, you have to work for your goal. Finally, you will achieve. And this is my normally my last slide. If you break a egg, a chick dies. But if the egg opens of its own, a life begins. So each one of you, you have lot of potential within you. Let it come out. You come as a good citizen and enjoy and be a good citizen of India. Thank you very much for listening and this one.
Thank you, sir, for
Well,
that.
yeah, now you can ask some questions if you want. Yeah. Yes.
Thank you, sir, for that deeply insightful and inspiring talk. Your remarkable journey and invaluable contributions to India's space program have truly motivated us. Your dedication, determination, and passion can drive innovation at any stage of life. You have inspired us to think big and take meaningful steps towards contributing to the future of science and technology. Your guidance and experience will certainly leave a lasting impact on young minds and shape our aspirations for the future. Sir, we have a question that what are critical factors in scaling engine trust while maintaining scalability, sir?
Huh? I didn't get what is that?
Uh,
What is that?
what are the critical factors in scaling engine trust while maintaining stability, sir?
Scaling the engine.
Yes, sir.
Okay. Combustion is the main thing when you are scaling up. So stability, combustion is not a very easy thing to maintain because if you are going bigger size engines and smaller, as I said, the temperature is very high. So thermal aspect to control, how to control the thermal aspect is very critical. Plus the material selection also very important. So these are all the factors when you are going. Of course, turbo machinery is a little easier because similarity factors can be easily workable. So you can make scale up can be done very easily for pumps and turbines and other things. But combustion chamber is a little difficult, specifically when you go for cooling with a lot of channels and other things and designing. Of course, currently a lot of tools are available and we can design, but still making a working engine with all these things are little complicated. So, in my opinion, combustion chamber design is little tricky when you are going for scaling up.
Sir, next I would like to invite Sneha to ask a question, sir.
Yeah. Yes, Nega.
Hi,
Yeah.
sir.
Yeah.
I'm Sneha, sir. So I would like to know what is the modern technologies like a 3D printing and private sectors involvement transforming rocket engine development, sir. So mostly I'm seeing 3D printing nowadays it becoming popular.
Yeah. I agree with you. 3D printing is coming very handy. But one for small engines, because nowadays in India, the bed size is only 400 by 400 by 500. So small engines easily we can print. But when you go for 110 engines and 210 engine, bigger engines, and we don't have that big size 3D printing machines yet to develop in our country. That is one point. Otherwise, today we have more than 4 or 5 good players on 3D printing. People are there in Mumbai, sorry, in Pune and Bangalore and Delhi and Chennai and all the 4 big towns, and they are good people. Even Hyderabad, I have not seen yet a good person. Maybe it will come very soon. And one good thing is like superalloy, like Inconel or whatever I talked about superalloy. It's very difficult to weld and form and all those things. But in 3D printing, it is in the powder form. So with a laser, with you give the three-dimensional
Sir,
printing thing. Yeah.
sorry for the interruption, sir. Can you stop sharing, sir, the screen?
I don't know how to do that.
So at the down here there will be stop sharing. Yeah,
Oh,
yes.
okay.
Thank you, sir.
So like that, if you even very complicated shapes, all those things can be done by 3D printing. For example, injector, if you take earlier days, there will be so many components and welding or bracing, all those things. Now everything in single piece we will make, and that we will make it all right. So like that, But in a bigger size, when it comes, we are now struggling to do what to do. Maybe the Americans right now they are having, but there are few techniques like for thrust chamber, like deposition technique. Now they are trying with RRL in DRDL facilities. Like that, improvements are coming, but currently it is not available for bigger engines to go for 3D printing. But for small engines, fine, we can go very fast. We can do that.
Glad to hear, sir. Thank you so much, sir.
Maybe you guys, now I said you MMH, sorry, UDMH and N2O4, it is not environment friendly. Now we are trying to develop green propellants, which is good for environment, like nitrogen tetroxide with ethane or propane. All these combination, I already tried in the new company with nitrogen tetroxide with ethane. I have fired. It has come very well. A small engine with 3D printing. It's good. So there are a lot of techniques, and you can also start working on that. Yeah. Somebody wants to raise again hand. Maybe Hasina. Anybody wants?
So one last question from the student Hasni, sir.
Yeah. Yes, Hasni.
Good evening, sir.
Yeah. Yes, madam. Yeah, I'm hearing.
Sir, in today's digital world, how to launch vehicles
Yeah. Yeah. You see,
develop
it,
ISRO
yeah, we are now
indirectly to
there are
support
a lot of
services?
safeties are there. If the rocket doesn't behave properly, it should not fall on earth, and it should not create any issue. So normally there is a rule. So we are now ISRO only helping all private companies to launch from Sririkota. That is point number one. Two, even though it is a digital world or whatever world you call it, we require a solid propellant to carry big cranes and all those things, and you have to build and you have to keep. It will take nearly about a month in Sririkota to build the rocket on the launch pad. Of course, towards the end, 2 or 3 days, it is totally digitalized and all are programmed. So propellant filling and this, that, and final countdown, all are digital. So no man, this one is involved. But initial 1 month, it is totally manual hard work. We have to carry and all those things. We have to do. Yeah. Of course, there are now systems are coming, portable launchers. We are also thinking for small satellite like our Vikram 1 or Vikram 2. We can take the launcher any place and lift it and launch, like Agni, for example, missiles. So we are also thinking of launching, but they may come. They have to permit. So that all in the pipeline. Maybe very few years that also will come. Thank you all for listening to me.
Thank you so much, sir, for encouraging young minds by giving answers to their questions. And I also thank each and everyone who showed interest in today's session by asking their questions. As we come to the close of this remarkable session, I invite Ms. Shruti to present vote of thanks. Ms. Shruti, over to you.
Good evening, respected dignitaries, honored speaker, teachers, and dear friends. I am Shruti, and it is my privilege to stand before you today to deliver the vote of thanks on behalf of KIYE Foundation and the Stock Lecture Series. I would like to begin by expressing our sincere gratitude to you, Vasudevan sir. Your presence today has been truly meaningful to all of us. The way you shared your journey and insights into space technology was not only informative, but quietly inspiring. It reminded us that great achievements are built step by step with clarity and dedication. Your words have sparked a sense of curiosity and possibility in all of us, sir. And for that, we are deeply thankful. I would also like to extend my thanks to the organizers for thoughtfully arranging this session. Opportunities like these allow us to look beyond textbooks and connect with real experiences. My
Thank you.
sincere gratitude is extended to our faculty coordinators for their continued support and gratitude. Your engagement plays a significant role in shaping our directions. To all the participants, thank you for your presence and engagement. It is your interest that brings life to sessions like this, and to everyone working behind the scenes. Your efforts have ensured that everything came together seamlessly. We are very grateful. As we conclude, I hope we carry forward not just what we learned today, but also the inspiration to aim a little higher and stay committed to our path. You may also stay connected with us through the social media platforms of KIYE for updates and upcoming initiatives. Thank you once again. Thank you, sir. Jai Hind.
Thank you, Shruti, for those wonderful words of gratitude. I would like to thank all the participants who joined us today. Your presence made this session truly meaningful. Thank you for being a part of Lecture 3 of S Talks. Let us continue this exciting journey together, exploring and discovering the world of science and space. And I request everyone to subscribe our YouTube channel, KIYE Foundation, for future sessions and also join our official WhatsApp channel for updates and announcements. Let's stay connected, stay curious, and keep reaching for the stars. Because theory, space is the next destination. Let's explore it together. Have a wonderful evening, everyone. Jai Hind.
Thank you.